This video is going to tell you how to go through and calculate the relative atomic mass. I'm going to tell you how to do it off a table, and then we're going to do it off a mass spectrum. So if you're not sure what I mean when I say mass spectrum, stop this video, go back and watch the other one on mass spectra. Okay, so what is the relative atomic mass? The relative atomic mass is that weighted mean of all of the masses of the isotopes of an element. So it's all good and well to say that there are 3 isotopes of carbon, but 98% of those isotopes are actually carbon-12. So you don't want to say that the average mass of carbon, if its isotopes are 12, 13, and 14, you don't want to say its average is 13. You want it to be a weighted mean, and because much, much more of it is this first one here, is carbon-12, then that's the one that we're going to have to weight our mean for, and it will figure out that our relative atomic mass of carbon is about 12.01. So just over 12, because there's some isotopes that are a bit heavier. So 2 symbols for this. You will see relative atomic mass as RAM, but you will also see it as an A with a subscript R. Now the units for this are just U or AMU. AMU stands for atomic mass units. Cool. Let's go on to our first example. So this is information that we pulled off that first mass spectra, the one that's in your notes on page 29. So we see that there are how many isotopes here? I have isotope 1, and I'm just going to change my pen color before this becomes difficult. This is isotope 1. This is isotope 2. Isotope 1 has got a mass of 35. Isotope 2 has got a mass of 37. Now, these are the actual masses if you read them off your nice and accurate mass spectra. So we call them 35 and 37, but when we measure them in atomic mass units, we're actually looking at a number that's just a little bit less than these. And over here we have their abundance. So what are we going to do with this? We're going to plug it into an equation. Now this equation is the AR, the relative atomic mass, is equal to the IR of the first isotope, which is here, multiplied by its relative abundance, plus the IR of the second isotope by its abundance, divided by 100. So just to save me having to write this out, what it would be good would be for you to pause and try and do this yourself, and then we'll go through the answers. So once we go through the answers, you can see here the relative isotopic mass has come from there, 38.969, and we multiplied that by its relative abundance, which is 75.8. So I'm just color coding it so you can see where all these numbers came from. Then we need to add the IR of the second one, which is over here, which is 36.966. And then we're going to multiply that by its relative abundance. Now, my question to you is, why are we going to divide by 100? These guys are in percentages. To get them out of percentages, we're going to have to divide by 100 to remove percentages. So I always like to draw out all of my workings. So I like to have my next step in here. So it says 20, when you multiply out that first bracket, you get 2,650.42 plus 894.58 over 100. When you plug that in, you end up with 35.45. Now, off your periodic table, you'll see that the AR of chlorine is equal to about 35.5. So this is very close. So therefore we go, yeah, we're good. We can use our periodic table to check. So this one here is a bit different. This time I've given you a mass spectra. I want you to pause, think about how you're going to attack this, and then restart in a minute. Okay, how many isotopes do we have? We have 2 isotopes. This here is their mass down the bottom. One is 10, one is 11, and here we have their percentage abundance. So to calculate my AR of boron, I'm going to need to multiply 80.1, which is the percentage, by 10, in brackets, times 19.9 times 11. Now, this is where I need to actually get out my calculator. 80.1 times 10. Oh, probably didn't need that. And all of this is divided by 100. So I'm going to show my workings. 801 plus 19.9 times 11 to 18.9. Add them together. Equals 1019.9. Divide by 100. And we end up with our AR of boron being 1.19, but I've only got 3 sig figs, so it should be 10.2. And there's your AR of boron. I'd suggest that you would pause and give this question a go. So you need to calculate its AR first, and then I want you to use your periodic table to figure out what it is. So you have a look at this. We can see that we have 3 isotopes this time. So I'm going to do this up here, just show my workings. So 9 times 70, yeah, plus 6 times 72, plus 1 times 74. Now, this time I'm not going to divide it by 100, because what is my total abundance of everything? It'll be 9 plus 1 plus 6 equals 16. So instead of dividing by 100 this time, I'm going to divide by 16, because that's the scale that I've been given. If this isn't in percentage, you need to be careful and add up each one of the abundances to figure out what we've got. So we've got 9 times 70 equals 630, plus 6 times 72 equals 432, plus 74. So I'm just going to plug them all in. And all of that's over 16. What we actually get is 1136 divided by 16 equals 71. Okay, so the AR of this element is 71. So then what do you need to do? You need to find your periodic table. So this is just going to take me 1 minute, girls, sorry, because I don't have one up. You can always fast forward me while I'm doing this. Periodic table. I'm going to look for one. Am I looking for the atomic number of 71, or am I looking for the mass number? That's right, I'm looking for the mass number. Of course, the one that I've picked up. So I go along and I can use the atomic number to help me. I reckon we're pretty close to the mass number for germanium. So it'll be GE. Okay, so mass number closest to GE. So that's what I'm going to say my element is. And that's where I'm going to stop that video.